Yes, we'll trace this curve. Y cube is equal to x square into 2a minus y. We have to trace this Cartesian curve. Y cube is equal to x square into 2a minus y. Now we can see that there are only even powers of x in this equation. There is no odd power of x in the equation. We have a term of x square. There is no term like x cube, x raised to 1, etc. So since there are only even powers of x in the given equation, the curve is symmetric about y-axis. Also, we can see that there is no even power of y in the equation. We are having some odd powers of y. Curve is not symmetric about the x-axis. जो symmetry नहीं है वो लिखने की जरूरत नहीं है. So we just have to write the symmetry which is applicable here. It is symmetric about y-axis. So we are also writing only about the symmetry about y-axis. The curve is not symmetric about x-axis. It is not necessary to write that. Now, if we check whether the curve passes through the origin, to check whether the curve passes through the origin, we'll put say x is 0 in this given equation. If you put x is 0 and y also becomes 0, then we can say that the curve passes through the origin. If I put x is 0 in this equation, we get y cube is equal to 0 into 2a minus y. We get y cube is 0, we get y is 0. That means when we can see that when x is 0, y also becomes 0. Therefore, the curve passes through the origin. So we could have done vice versa also. We could have substitute y as 0 in the given equation. You will find x also becomes 0. So the curve passes through the origin. Also, see, there is one more rule which says that if there is, say, if there is a absolute constant in the equation, then the curve does not pass through the origin. Now, see, there is no absolute constant in this equation. See, there is a constant 2a, but if you open the bracket, it will become 2a into x square. So that constant is multiplied with a variable x square. So this cannot be called as an absolute constant. The absolute constant is a constant which is not multiplied by any variable x or y. So also, since there is no absolute constant in the given equation, therefore the curve is going to pass through the origin. So this is an alternative rule you can apply to check whether the curve passes through the origin. Then see, since the curve passes through the origin, we must find tangent at origin. So to find tangent at origin, first consider the given equation, which is y cube is equal to x square into bracket 2a minus y. If you open this bracket, it becomes y cube is 2a x square minus x square y. Now see, y cube, we know degree of y cube is 3. Then this term x square into y, degree of this term is also 3 because it is x square into y, that is x square into y raised to 1. We add the powers, 2 plus 1 becomes 3. So degree of x square into y is 3. If you consider this term 2a x square, 2a is a constant of which degree is considered 0, x square degree is 2. So 0 plus 2 is 2. So degree of 2a x square is 2. Now we know to find tangent at origin, we have to equate the lowest degree term in the equation with 0. Tangent at origin find करने के लिए हमें करना क्या होता है, गिवन इक्वेशन में जो लोएस्ट डिग्री टर्म है, जो सबसे कम डिग्री वाली टर्म है, उसको 0 के साथ इक्वेट करना होता है. ये जो 2a x square है, लोएस्ट डिग्री टर्म, उसको हम 0 के साथ इक्वेट करेंगे. We equate 2a x square with 0. We know that it will mean that x square is 0. See, 2a is a constant, so that cannot be 0. So we take x square as 0. X square is 0 will give us x is 0. And you will find, see, x square is 0. So that means x into x is 0. We are going to get x is 0 2 times. Remember, x is 0 is nothing but y-axis. So y-axis is the tangent at origin in this case. And now since we are going to get x is 0 2 times, it means y-axis will be tangent to the curve 2 times. Or in other words, it is going to be a cusp. So we know that if we get two coincident tangents at the same point, then it becomes a cusp. So y-axis is tangent to the curve at the origin, and it is going to be a cusp because we are reading x is 0 2 times there as the tangent. Now to find asymptote, see, to find asymptote parallel to x-axis, we have to equate the coefficient of highest degree term in x with 0. So see, to find asymptote parallel to x-axis, we have to equate the coefficient of highest degree term in x with 0. See, here this is the highest degree term. So this term x square. So there is only one term of x, that is x square. So that is the highest degree term of x, and coefficient of that is 2a minus y. So according to this rule, to find asymptote parallel to x-axis, we have to equate the coefficient. What we have to equate? Coefficient of what? Coefficient of the highest degree term in x. Highest degree term in x is x square. Coefficient of that is 2a minus y. And if we equate with 0, we get 2a minus y is 0, or we get y is equal to 2a. So that is the asymptote to the curve. Now remember, this is the line y is 0, that is our x-axis, and y is 2a is a line parallel to x-axis. That is going to be asymptote to the curve. The curve is going to run parallel to this line y is 2a, it will not touch that line. It will touch that line only at infinity, we can say, according to the definition. We have found out asymptote as y is 2a, asymptote parallel to x-axis. Then to find asymptote parallel to y-axis, we have to equate the coefficient of highest degree term in y with 0. In this equation, highest degree term in y is y cube and coefficient of that is 1. If we equate 1 with 0, we'll get it as meaningless. 1 is 0 is meaningless. So see, highest degree term in y is y cube, coefficient of that is 1. 1 is equal to 0 is meaningless. Therefore, there is no asymptote parallel to y-axis in this case. Now, next, if you find the region of absence, see, if you find region of absence, automatically we get the region of presence also, like where the curve is present and where the curve is not present. The region where the curve is present, we'll call it as region of presence, and where it is absent, we'll call it as region of absence. For that, see, we consider the given equation. The given equation is x square is equal to y cube upon 2a minus y. See what I have done? The given equation y cube is x square into 2a minus y. I have rearranged and I have written it as x square is equal to y cube upon 2a minus y. Cross multiplying. So I express the equation in the form x square is some function of y. Whenever possible, we express the given equation either in the form x square is some function of y or y square is some function of x. Here we are able to express in the form x square is some function of y. Now, what is the use of this? From this we can identify for what values of y the numerator becomes 0 as well as the denominator becomes 0. The numerator of this equation becomes 0 when y is 0. If I put y is 0, numerator will become 0. So see, I have drawn this line y is 0, that is nothing but the x-axis. Then the denominator becomes 0 when y is 2a. And if I substitute y is 2a, the denominator becomes 0. So I have drawn this line y is 2a. So I have drawn these two lines, y is 0 and y is 2a. What is the use of drawing these two lines? See, these two lines divide this region into three parts. Which three parts? Y less than 0. So that is the region below the line y is 0, region below x-axis. When we say y is less than 0, it means y will have some negative values, like y can be minus a, minus 2a, minus 3a. Okay. And then the second region is between the two lines, y is 0 to y is 2a. That is between 0 to 2a. 0 less than y less than 2a. So there y can have values like 0.5a or a, 1.5a, 1.9a, etc. And we'll get one more region, that is y more than 2a, like y is 3a, 4a till y is infinity. So these two lines divide the region, divide this space of this board, we can say, into three parts. Now we'll get the region of absence in either of these three parts, or say also the region of presence is going to lie somewhere in between these three parts only. To check that, again consider this equation that x square is y cube upon 2a minus y. Remember, the region where x square is positive will be region of presence, and the region where x square will be negative will be region of absence. Now to check that, consider the first region, y less than 0. You can consider any value of y which is less than 0. Here I have considered y is minus a. You can take y is minus a, minus 2a, etc. Any negative value of y. And substitute in this equation. In place of y, if I write minus a, see, x square will be cube of minus a upon 2a minus of minus a. It is minus a cube upon 2a plus a. So it is minus a cube upon 3a. So it becomes minus a square by 3. Now, see, x square we are getting negative. X square is negative for this region, y less than 0. X square is negative in that region. That means that region is region of absence. See, we are interested in only finding whether x square is positive or negative. We are not interested in this magnitude, remember. X square is negative just implies that that region y less than 0 is a region of absence. Similarly, for the second region, 0 less than y less than 2a, consider any value of y. Like here I have considered y is equal to a, some value of y between that region 0 to 2a. We consider some simple value, y is 8. Don't consider any complicated value like y is 0.9a, etc. Take some simple value. Our aim is just to check whether this x square becomes positive or negative in that region. So if I put y is a in this equation, it will be a cube upon 2a minus a. Simplifying, it comes out as a cube upon a, that becomes a square. X square is positive. See, our aim is checking whether it is plus or minus. It is positive. X square is positive in that region. It means it is region of presence. That means the curve will exist. It is the region of existence for that curve. Then consider that last region, y more than 2a. You can take some value of y as say 3a and substitute in this equation. it becomes a 3a cube upon 2a minus 3a. Numerator will be positive, denominator 2a minus 3a becomes negative. Positive upon negative becomes negative. X square we can see is negative in the region y more than 2a. So it is a region of absence. So see, we have seen that the region y less than 0 is region of absence. The region below x axis is region of absence. Y more than 2a, the region above the line y is 2a is region of absence. Whatever is the curve is going to draw. We have to draw within these two lines. We have seen that the curve is symmetric about the y-axis. Since there are only even powers of x, is symmetric about y-axis. So whatever is the nature on the right hand side of y-axis, same will be the nature on the left hand side of y-axis. We have seen that the curve passes through the origin, and we have seen that this y-axis, that is x is 0, is tangent at origin. While finding tangent at origin, remember we had got x square is 0, we had got x into x is 0. 2 times this y-axis is tangent to the curve, or we are going to get a cusp at that point. Also, we have seen y is 2a. Line y is 2a is asymptote to the curve. Is asymptote to the curve. That means curve is going to run parallel to this line. So see, keeping this in mind, we draw the curve. So see, first of all, we know that the curve will pass through the origin, and this line y-axis tangent at origin, and this line y is 2a is asymptote to the curve. So our curve is going to run parallel to this line. So see, it is going to look something like this. Remember, we are drawing an approximate curve. I'm not measuring any distances. So I'm drawing the curve in such a way that y-axis is tangent to the curve at origin, and then further this y is 2a is an asymptote. That means our curve will run parallel to the line y is 2a, and we know that the curve symmetric about the y-axis. So whatever is the nature on the right side of y-axis, same will be the nature on the left hand side of y-axis. So y-axis tangent to the first as well as second branch of this curve to this point will be called as a cusp. This is a cusp. This is how the curve will look like. I hope you have followed this.